light-years away, visible in data only through the faint heat signature of the light it has absorbed. It is known to us almost entirely through what it is not. Not reflective, not bright, not visible, not there, in any ordinary sense, until the mathematics says otherwise. It is the 12th place on tonight's list, a world that has spent its entire existence swallowing light and giving nothing back. Not out of malice, not out of anything, simply because that is what the chemistry produces when temperature and composition align in this particular way. The universe did not intend the dark planet to be dark. It just turned out that way. The 13th place on tonight's list is a moon, chaotic, irregular, unpredictable, a moon that tumbles through space with no fixed orientation, spinning in ways that no model can fully anticipate, belonging to a planet that is itself one of the strangest objects in our solar system. There is something philosophically interesting about the dark planet. If you sit with it long enough, we find the universe through light, through the light stars emit. The light planets reflect. The light that travels across billions of years to reach our instruments. Almost everything we know about the cosmos came to us as light of one kind or another. The dark planet is a reminder that the universe contains things that do not participate in that exchange. Things that take the light in and return nothing. Things that are there, fully and completely, but that choose, if choosing is even a word that applies, not to be seen. The universe is full of things we cannot see. The dark planet is just one of the more literal examples. The 13th place on tonight's list does not know which way it is facing. That is not a poetic description. It is a precise one. Hyperion, a moon of Saturn, roughly the size of a large city, shaped like a potato that has been squeezed unevenly and then left to cool, is in a state of genuine, mathematically confirmed chaos. Its rotation cannot be predicted, not because we lack data, not because our instruments are imprecise, but because the physics governing its spin is fundamentally, irreducibly chaotic in the technical sense, meaning that tiny differences in initial conditions produce completely different outcomes over time. And no amount of calculation can tell you with certainty which way Hyperion will be oriented at any given moment in the future. It tumbles. That is the word scientists use. Hyperion tumbles through space. Most moons in our solar system are tidally locked, like our own moon. They rotate at the same rate as they orbit, so one face always points toward their planet. Hyperion refuses. Its orbit around Saturn is irregular enough, its shape lopsided enough, and the gravitational tugs it receives from Saturn and from the nearby Moon-Titan complex enough that it cannot settle into a stable rotation every time it approaches a configuration that might become regular. Something perturbs it, a slightly stronger gravitational pull, a fractional asymmetry in its own mass distribution, and the tumble shifts. The axis changes. The orientation jumps to something new. Over the course of a single orbit around Saturn, which takes about 21 days, Hyperion can change its rotational axis significantly. If you were standing on its surface, the sky above you would wheel in ways that have no pattern you could memorize or predict. Saturn would rise and set on no schedule. The sun would move across the sky differently every day, because the day itself, defined by the moon's rotation, has no fixed length and no fixed relationship to the orbit. Hyperion is also visually extraordinary in a way that has nothing to do with its chaotic spin. Its surface is covered in craters, deep, sharp-edged craters that have not been smoothed by the geological processes that reshape surfaces on more active bodies. But these craters are not the round, bowl-shaped impacts you see on the Moon or Mars. They are deep and angular, with walls that descend steeply into dark interiors. The overall effect, seen from above, is a surface that looks almost sponge-like, a network of interconnected hollows separated by sharp ridges, covering the entire body in a pattern that has no clear equivalent anywhere else in the solar system. The reason for this unusual crater morphology is Hyperion's density, or rather, its lack of density. Hyperion is extraordinarily porous. About 40% of its volume is empty space, gaps and voids within the interior, making the whole body more like a loosely packed aggregate than a solid rock. When something strikes Hyperion, the impact does not splash material outward the way it would on a denser body. Instead, it compresses the porous interior, driving material downward and inward, creating those deep, steep-walled craters that give the surface its sponge-like appearance. A moon like a sponge, tumbling, unoriented, shaped like nothing in particular. What Hyperion represents, in the broader context of how we think about moons and planets, is a reminder that orderly rotation, the kind that gives Earth its days, that gives our moon its fixed face toward us, is not inevitable. It is an outcome arrived at over millions or billions of years of gravitational interaction, and it requires the right conditions to emerge. Hyperion has the wrong shape, the wrong mass distribution, and the wrong orbital environment for orderly rotation to take hold. It has been tumbling, apparently, since it formed. And unless something dramatic changes its situation, it will keep tumbling indefinitely. There is something unexpectedly freeing about that, if you choose to see it that way. Most things in the solar system have settled into predictable rhythms. Planets orbit in nearly circular paths. Moons lock their faces toward their planets. Asteroids spin at rates that can be measured and predicted. The universe, at the scale of our solar system, has mostly sorted itself into regularity. Hyperion did not get the memo. It orbits Saturn on its own chaotic schedule, pointing at nothing in particular, answering to no fixed orientation, tumbling through its 21-day orbit as freely as anything in the solar system tumbles. It does not know it is chaotic. It does not know anything. It simply responds to the forces acting on it. Gravity from Saturn, gravity from Titan, the asymmetries of its own shape. And the result of all those responses, added together, is a rotation that no equation can fully capture in advance. The 13th place on tonight's list is a moon that has never found its footing. And in the vast, patient solar system, it keeps tumbling anyway. The 14th place on tonight's list is not a place you can see. It is a force, or rather, the evidence of a force. Something that is pulling our entire galaxy, and thousands of galaxies around it, toward a single point in the sky, pulling everything, relentlessly. and we cannot see what is doing it. There is one more detail about Hyperion that tends to stay with people: its color. Hyperion is not the gray of most rocky moons, not the reddish tones of iron-rich surfaces, not the white of ice. It is a dark, mottled brownish red, stained. Scientists believe by complex organic molecules called tholins, formed when ultraviolet light from the sun interacts with the nitrogen and methane that drift through the outer solar system. The same reddish tint appears on the surfaces of distant objects throughout the outer solar system, a signature of chemistry happening slowly, in the cold and the dark, over millions of years. Tholins, the universe's own slow-brewed organic chemistry, painting the surfaces of chaotic, tumbling moons in colors we are only beginning to understand. The 14th place on tonight's list is pulling you right now. Not metaphorically, not in the way that gravity pulls everything toward everything else in a general, diffuse sense, something specific, something enormous, something located in a specific direction in the sky, roughly toward the constellation Centaurus, slightly south of where the Milky Way is thickest, that is drawing our galaxy, and hundreds of galaxies around it, toward it at a speed of roughly 600 kilometers per second. 600 kilometers per second. Every second that passes, the Milky Way moves 600 kilometers closer to whatever is there. We call it the Great Attractor. And what makes it one of the strangest places on tonight's list is not its size or its gravity, or even the scale of the motion it is causing. What makes it strange is that we cannot see it. The Great Attractor sits almost perfectly behind the densest part of the Milky Way's disk, the region where gas and dust are thickest, where visible light is completely blocked. Everything we know about it has been inferred from the motion of galaxies around it. From radio waves and X-rays and infrared observations that can penetrate the dust where visible light cannot, we are being pulled towards something we cannot look at directly. We have been pulled toward it for the entire history of our species, and for billions of years before that. And we will continue to be pulled toward it for billions of years to come. To understand what the Great Attractor probably is, you have to think about structure at the largest scales. Galaxies, as we discussed when we visited the cosmic web, are not distributed randomly. They cluster, and those clusters themselves cluster into larger structures called superclusters. Our galaxy belongs to a supercluster called Laniakea, a structure 500 million light-years across, containing the mass of 100 million billion suns, of which our entire Milky Way is a tiny, peripheral part. The Great Attractor sits near the center of Laniakea. It is not a single object, not a black hole, not a galaxy, not even a galaxy cluster in the ordinary sense. It is a concentration of mass, a region where multiple galaxy clusters have gathered, where the total gravitational pull is large enough to influence the motion of everything within hundreds of millions of light years. Think of it less as a thing and more as a place, a gravitational basin into which the surrounding universe is slowly draining. And yet, even the Great Attractor is not the final answer. Astronomers studying the motion of galaxy clusters across even larger scales found that the Great Attractor itself is moving, not stationary at the center of Laniakea, moving toward something even more massive, even further away, a structure called the Shapley concentration, 650 million light-years from Earth. The Shapley concentration is the largest known concentration of galaxies in the observable universe. And the Great Attractor, enormous as it is falling toward it along with everything else. There is a chain here that keeps extending. The Milky Way falls toward the Great Attractor. The Great Attractor falls toward the Shapley concentration. The Shapley concentration itself is presumably moving toward some even larger mass concentration that we have not yet fully mapped. The universe is not static. It is not settled. At every scale we examine, things are moving, falling toward each other, pulled by gravity, organized into flows that we are only beginning to trace. What does it feel like to know this? To know that the galaxy you live in, the 100 billion stars of the Milky Way, the 4 billion years of Earth's history, every life that has ever been lived on this planet, is currently moving at 600 kilometers per second toward a gravitational concentration you cannot see, in a direction you cannot look? For most people, it does not feel like anything immediately. The motion is too large, too slow by everyday standards, too abstract to register in the body. You are moving at 600 kilometers per second toward the Great Attractor right now, and you feel nothing. The room around you is perfectly still. The coffee cooling on the nightstand is perfectly still. Everything is perfectly still. And yet the motion is real. The pull is real. The Great Attractor is real. Even if we cannot see it, even if we cannot name precisely what it is, even if the full picture of what is drawing us toward it is still being assembled from data that takes decades to collect and longer to understand. The 14th place on tonight's list is a gravitational presence so large it moves galaxies. It has been moving our galaxy for billions of years. It will keep moving it long after anything on Earth can notice. The 15th place on tonight's list is a star. Just a star, nothing as dramatic as a black hole or a cosmic web or an invisible gravitational giant. But this star has a problem. According to the best measurements we have, it is older than the universe that contains it. There is something quietly vertiginous about the Great Attractor. Not the fear of falling, but the realization that falling has been happening all along, at a scale too large to feel. We think of the sky as fixed. We think of the stars as permanent. We think of the galaxy as something stable, something anchored. The Great Attractor is a reminder that none of that is quite true. Everything is in motion. Everything is falling toward something. The stillness is borrowed. The anchor is somewhere we cannot see. 600 kilometers per second. Right now, while you lie still. The 15th place on tonight's list should not exist. That is not a rhetorical flourish. It is the conclusion that astronomers arrived at when they first calculated the age of this star, a conclusion so uncomfortable that they spent years checking and rechecking the measurements, hoping to find an error somewhere that would make the number come out differently. No error was found. The Methuselah star, named for the oldest person in the Bible, said to have lived 969 years, appears, by the best measurements currently available, to be approximately 14.5 billion years old. The universe is 13.8 billion years old. That gap, 700 million years, is the problem. A star cannot be older than the universe that produced it. The universe existed before any star did. Stars formed from the gas and dust that the Big Bang created. After that gas and dust had time to cool and collapse, which took hundreds of millions of years. For the Methuselah star to be 14.5 billion years old, it would have had to form before the universe was old enough to form stars, which is not possible. And yet the measurements say what they say. The Methuselah star sits about 200 light years from Earth, close by stellar standards. Close enough that we have been able to study it in unusual detail, measuring its composition, its luminosity, its distance, its motion through space. It is a very old star by any measure. Its composition shows almost none of the heavier elements that younger stars contain, because those heavier elements did not exist in the early universe. They had to be forged in earlier generations of stars and distributed through the galaxy by supernova explosions. The Methuselah star, formed before many of those earlier stars, had time to live and die. It is, without question, among the oldest stars we know of. The question is exactly how old. Stellar age is not something you can read directly. You cannot look at a star and count rings the way you count rings in a tree trunk. Instead, astronomers infer age from a combination of measurements: the star's luminosity, its temperature, its composition, its distance, and feed those measurements into models of how stars evolve over time. The models are sophisticated and well-tested, but they depend on assumptions that carry uncertainties. The distance to the star, for example, affects the luminosity calculation, which affects the age estimate. A small error in the distance measurement produces a larger error in the age estimate. When astronomers account for all the uncertainties, the measurement errors, the model assumptions, the range of plausible values for each parameter, the age of the Methuselah star comes out as 14.5 billion years, plus or minus about 800 million years. At the lower end of that range, 13.7 billion years. The star is just barely younger than the universe, just barely possible. The measurements and the cosmology could, at the edges of their respective uncertainties, be consistent with each other. Just barely. This is where science lives. Sometimes, not in clean answers, but in the overlap between uncertainties. Not in the comfortable space where everything agrees, but in the uncomfortable margin where what we measure and what our models predict are almost, but not quite, the same. The Methuselah star is the universe asking us to be more precise, asking us to measure better, model better, understand better. Until the gap between 14.5 billion years and 13.8 billion years either closes or forces us to revise something fundamental about what we think we know. There is a kind of grandeur in that. A single star, 200 light years away, quietly burning for longer than the universe should have allowed, and by its mere existence posing a question that the best physics in the world has not yet fully answered. The Methuselah star formed when the universe was young, incomprehensibly young by current standards, before the Milky Way had fully assembled, before most of the stars in the night sky existed. It has watched the galaxy form around it. It has watched generations of stars ignite and burn and explode and scatter their elements across space. It has watched the solar system assemble from that scattered material, watched Earth cool and develop its oceans, watched life emerge and diversify, and eventually produce creatures capable of looking up and measuring how old things are. And it is still burning, still there, a dim, ancient subgent, spending the last fraction of its long life slowly expanding as the hydrogen in its core runs low. In cosmic terms, it does not have much time left. A few billion years. It has already spent more than the universe's current age, possibly more than the universe's current age, getting to this point. What the Methuselah star offers, in the quiet of tonight, is a reminder that the universe keeps score in ways we are still learning to read, that the numbers we are most confident in sometimes sit in tension with each other, that the oldest things in the sky carry questions we have not yet finished asking. The 15th place on tonight's list is a star that outlived the possible, and it is still there, still burning, 200 light years away, in no particular hurry to explain itself. The 16th place on tonight's list is not a star or a planet or a void. It is a sound. Or rather, what sound would be if the universe had made it at the very beginning, and the echo of it were still reaching us now, filling every corner of the sky in every direction, all at once. The 16th place on tonight's list is everywhere. Not in one direction, not concentrated in a region of the sky you could point to. Everywhere, above you, below you, in every direction simultaneously, filling all of space with equal intensity, arriving at your skin right now from every angle at once. You cannot see it with your eyes, but it is there. It has been there since before the earth existed, since before the sun ignited, since before any star in the observable universe had formed. It is the oldest light we can detect, the echo of the universe's earliest moments, still traveling, still arriving, still present in every cubic centimeter of space that exists. We call it the oldest light, the faint glow left over from the universe's infancy. To understand what it is, you have to go back further than any of the other places on tonight's list have taken us. Further than the Methuselah star, further than the cosmic web, further than the Big Bang itself, to the moment. Approximately 380,000 years after the Big Bang, when the universe cooled enough for something extraordinary to happen for the first time. Before that moment, the universe was too hot for atoms to exist. The energy was so intense that any electron that tried to bind to a proton was immediately knocked away. The universe was a plasma, a fog of free electrons and protons and photons, all colliding with each other constantly. The photons unable to travel more than a short distance before being scattered by another free electron. The universe was opaque. Light could not move freely through it. If you had been there, which you could not have been, you would have seen nothing in any direction. Just a dense, hot, glowing fog with no structure and no transparency. And then the temperature dropped below a threshold. The electrons slowed enough to bind to the protons. Hydrogen atoms formed, the first atoms in the history of the universe. And the moment they formed, the fog cleared. The photons that had been trapped in the plasma, scattering endlessly off free electrons, were suddenly free. They streamed outward in all directions, the first light to ever travel freely through the universe, released all at once from every point in space simultaneously. That light has been traveling ever since, for 13.8 billion years. Those photons have been moving outward, stretching as the universe expanded, cooling as they stretched, from the intense heat of the early universe down to just under 3 degrees above absolute zero. The temperature they carry today, they are no longer visible light. They have been stretched by the expansion of space into microwave radiation, the same frequency used by microwave ovens, but so diffuse and so cold that the total energy reaching any square meter of Earth's surface is a tiny fraction of what a candle produces. And yet, they are everywhere. The oldest light arrives at Earth from every direction in the sky with almost perfect uniformity. The same temperature, the same intensity. No matter which way the instruments point, almost perfect. Not quite. The tiny variations, fluctuations of about 1 part in 100,000, are the most important thing ever measured in cosmology. Those variations are the fingerprints of the density fluctuations in the early universe that we discussed when we visited the cosmic web, the slight unevenness in the plasma that, over billions of years, gravity turned into galaxies and filaments and voids. Every galaxy that has ever existed, including the Milky Way, including every star you have ever seen, traces back to those tiny fluctuations encoded in the oldest light. The pattern of the oldest light is the blueprint from which everything was built. Astronomers have mapped it in extraordinary detail. Satellites launched specifically to study it have measured the temperature of the oldest light across the entire sky, producing maps of those tiny variations that look, at first glance, like abstract art, patches of slightly warmer and slightly cooler radiation distributed across a circular image of the full sky. Those patches are the seeds of structure. Those patches became everything. What stays with you about the oldest light, what tends to surface at quiet moments after you have learned what it is the intimacy of it. It is not something out there, in some distant region of space that you might someday visit. It is here. It is on your skin, right now. Photons that have been traveling since 380,000 years after the Big Bang are landing on you, on the back of your hand, on your face, on every surface that is exposed to open space. You are, at this moment, being touched by the oldest light in the universe. It does not feel like anything. The energy is too low, the photons too diffuse, the interaction too gentle to register as sensation. But the contact is real. The oldest light has crossed 13.5 billion years of expanding space to reach this room, this moment, this particular point in the long story of the universe. And it arrives the same way it has always arrived, from everywhere at once, without fanfare, without preference, touching everything equally. The 16th place on tonight's list is not a place you travel to. It is a place you are already in. You have always been in it. The oldest light was waiting here before you arrived. The 17th and final place on tonight's list is the place where all of this ends. The edge of everything we can ever know. A boundary written into the physics of the universe itself, beyond which no information can reach us. No matter how long we wait or how powerful our instruments become. The 17th and final place on tonight's list is the one you can never reach. Not because the distance is too great, though it is. Not because the technology does not exist, though it does not. But because the universe itself has written a boundary into the physics of space and time. A limit that is not a wall you could approach and touch, but a horizon that recedes as you move toward it, defined not by what is there, but by how fast space is expanding between here and there. We call it the edge of everything, the boundary of the observable universe. Here is what it means. The universe began about 13.8 billion years ago. Light travels at a fixed speed, roughly 300,000 kilometers per second, the fastest anything can move. That means the furthest light could possibly have traveled in the age of the universe is 13.8 billion light years. Any object beyond that distance could not have sent us a signal that has had time to arrive. We cannot see it. We cannot know it exists. Not because it does not exist, it almost certainly does, but because the light from it has not had enough time to reach us. That would make the observable universe 13.8 billion light years in radius. But it is actually larger than that, about 46 billion light years in radius. The reason is expansion. The universe has been expanding since the Big Bang, and the regions of space that emitted the light we are now receiving have moved further away in the time it took that light to travel. The math is precise. The geometry is strange. And the result is a sphere of observable universe about 93 billion light years across. Beyond that sphere, in every direction, in a shell that begins where our observation ends and extends outward indefinitely, is everything we cannot see, everything we will never see, not because of any temporary limitation, but because of a permanent one. The expansion of the universe is accelerating. The space between us and those distant regions is growing faster than light can cross it. Objects beyond a certain distance are, right now, receding from us faster than the speed of light, not because they are moving through space at that speed, but because the space between us and them is expanding at that rate. This means that any object beyond our cosmic horizon is not just currently invisible, it is permanently invisible. The light it emits today will never reach us, because the space it must cross is expanding faster than the light can travel across it. Every moment that passes, more of the universe crosses that horizon, not by moving, but by the expansion carrying it away. The observable universe is, in this sense, slowly shrinking relative to the full universe, even as the full universe itself grows. No one knows how large the full universe is. It may be finite, bounded. In some geometry we do not fully understand. It may be infinite, extending without limit in all directions, filled with matter organized into structures like the ones on tonight's list, repeating in variations we will never know about. The honest answer is that we cannot know. Our instruments can only reach as far as light has had time to travel, and everything beyond that boundary is, by definition, beyond knowledge. This is the thing the edge of everything does that none of the other places on tonight's list quite manage. The diamond planet is strange but knowable. The water world is alien but measurable. even the great attractor, invisible behind the galactic plane, is something we have inferred and mapped and given a name. The edge of everything is different. It is not strange in the way that other things are strange. It is the boundary of strangeness itself, the point beyond which the universe stops being something we can describe, not because we have not looked hard enough, but because looking is not possible. And yet it is not a bleak boundary. There is something clarifying about it. If you approach it the right way, the universe has given us a finite window, 93 billion light-years of observable space, 13.8 billion years of observable time. And within that window, there is enough. Diamond planets and glass rain and tumbling moons and a web of galaxies that looks like thought and a star older than the universe should allow. Enough strangeness for a lifetime. Enough wonder to fill every quiet night until the last one. The edge of everything is not an ending. It is the shape of what we have been given. It is the frame around the picture. And the picture, as tonight has tried to show, is extraordinary. The 17th and final place on tonight's list is the place beyond which the list cannot go. The universe drew a circle around what we can know, and inside that circle, it placed 17 places strange enough to fill a night, and billions more we have not yet found names for. We have come a long way tonight, from a planet of diamonds 41 light-years away, through iron rain and glass storms and a moon that tumbles without pattern, through the center of our own galaxy and the web that holds all galaxies together, through a star older than time and a light that has been traveling since before the Earth existed, all the way to the edge of everything, where the universe ends not with a wall, but with a horizon, and beyond the horizon, more universe than we will ever see. It is enough to lie still in. It is enough to drift inside. The list is complete. 17 places. A diamond planet and a glass storm and a moon that tumbles without knowing it. A star spinning at the edge of its own destruction and a void where 2,000 galaxies should be and are not. A wanderer that has never seen light. A web that looks like thought. A black hole at the center of everything you have ever looked up at. A star older than the universe that contains it. And a light so old, it was there before the Earth existed, still arriving, still touching you. Right now, in this room. The universe is not required to make sense at human scale. It never has been. It builds what the physics allows, leaves it running, and moves on. The diamond planet did not ask to be extraordinary. The dark wanderer did not choose its path. The oldest light did not decide to travel for 13 billion years toward this particular room on this particular night. Things simply are what they are. At the scale they are, for as long as they last. And somehow, from inside, one small planet, in one ordinary solar system, in one peripheral corner of one galaxy among hundreds of billions, we looked up. We built instruments. We learned to read the light. We found the diamond planet and named it. We traced the motion of galaxies back to an invisible attractor. We mapped the oldest light and found the seeds of everything inside it. That is not nothing. That is, in fact, something extraordinary of its own kind. You are part of a universe that made diamonds fall from the sky on a world 41 light years away, and also made something capable of knowing that. Both things are true at the same time. The strangeness is out there, vast and indifferent. The awareness is in here, small and improbable. And tonight, for a few hours, the two of them sat together in the dark. Thank you for being here at Nightward. The universe will keep running while you sleep. The iron will keep falling on the night side of the Iron Rain planet. Hyperion will keep tumbling. The oldest light will keep arriving. The edge of everything will keep receding. None of it needs you to watch. Rest now. The strange places will still be there in the morning.